All right. I'll try to get at least one more reading in. I just did my workout. I did it while watching an episode of Star Trek. It actually took me the whole episode to do it. So um, I wanted to do 500 reps of just my shoulder rotations, but I ended up doing a total of 900. I was going to do 20, 40, 60, 80, 100, 80, 60, 40, 20. But instead, I ended up doing 10, 20, 30, 40, 50, 60, 70, 80, 90, 80, 70, 60, 50, 40, 30, 20, 10. Which, if I did the math right, adds up to 900. So that's 2,700 total arm motions, 900 in three different directions. So that's pretty crazy. God. I don't know how long I'll be able to stay up, though. So my goal is to try to get one more reading in. Let's see how that goes. We're on 12:04. What? Oh, I guess it is. Go ahead and pause that. Let's let that go until maybe 3 or 4. So I'll have to get up and press the button a few times. But with the way I've been sleeping, I can enter full REM state after the first time. So second time, third time, so on. I can re-enter in less than 5 minutes. So at least that's what it feels like. It feels quick. All right, well, I'm going to throw my headphones on. I'm going to go ahead and start drowning out the noise. All right. Go. How many videos have I done so far? 85. Nice. That's pretty amazing. And each one is, half an hour to an hour long. So that's almost 40 to 80 hours in the last few weeks. I think I started. Let's see. Let's get rid of that. Let's go to the end. August 28th. Yeah, so it's been less. It's only been a couple weeks. That's crazy. Yeah, I'm gonna keep that. That's pretty sweet. Oh, that's crazy. Only in 2 weeks. It feels like it's been forever. That's amazing. And I have my final plans in mind. But like the way I like to think of it, like a shadow, the only visible part of the shadow is the part that hits the surface. That's opposite or 180 degrees away from the source of the light or the primary source of light. So um, I lost my train of thought there. Might have to grab some coffee. Oh, I was thinking though, for sleep, because I'm trying to see if I can make the Uberman schedule work, where it's 6 20-minute naps per day. But I'm struggling getting straight into it, so I'm thinking of creating a transition state to help me get into it. And I was thinking of once I'm done with work for the day and I'm ready to connect, maybe after like 8 o'clock, I'll connect, lay down for like 2 or 3 hours. It seems like when I go to bed after pushing myself physically, I get up It's a really quick sleep. The dream is minimal. I don't even notice it half the time. And then I just get up and I just start doing this. I think this should be the start of my day, doing the education stuff and then going to work and then coming home, relaxing for a little bit and then sleeping for a little bit. Or maybe doing um, doing the full Uberman sleep schedule at night. Because the thing is when I'm exercising, that usually keeps me going. That usually gives me energy, and I can usually push myself further. Like with the exercise I just did. Um, yeah, with the exercise I just did, my plan was to do like half of what I did, and I just kept pushing it. And because I had my mind distracted watching the episode of Star Trek, it was much easier for me to keep doing it. So that'll be an interesting one. I might be able to make something out of that work, or to make something work out of that. Um, so I think so tomorrow, or I guess today, my goal is to set. Um, see to see if I can make. I'd like to see if I can make $300 or $400 in a day. I can work the hours. I just got to start early. The problem is I start late, and then I convince myself not to go half the time. So I just need to get myself out there. So I think I need to bring something with me that I can work on. So I think I'm just going to bring a dictionary and my voice recorder, and I'm just going to read pages of the dictionary. I know that sounds silly, but I want to get that podcast started using this. So basically, I'll record 150 to 160 hours worth of content and then upload it all at once because the file size won't be crazy big. I guess actually it actually would be kind of big, but um, it's divided, so I could just upload it. Spend a day uploading while studying and recording other stuff. See that just makes more sense to me, and then that way I'm not wasting time. I'm actually making the best use of my time. So this is what I'm thinking. I'll just write it down real quick, so that way it's easier to understand. Here, so completions. Let's do 917 workout. So that's type, and shocked face, and then description. And then that's going to be an open mouth. This is going to be shoulders, shoulder trinity, 10, 20, 30, 40, 50, 60, 70, 80, 90, 80, 70, 60, 50, 40, 30, 20, 10. And I'll call that the 10. 1 through 9 through 1. Shortcut. So basically, because I'm obsessed with languages, and especially the English language, because that's the only one I know right now. Well, and then also specialty languages like chemistry, physics, and all that stuff. Um, what I just did was I basically created a word. This means the workout that I did, that specific workout. That word has meaning to me, but I wrote it in the form of a number. But saying uh, 10 open, 1 by 9 by 1 close. That's the rep setting. So cool. I like that a lot. Why did I come here again? Oh yeah. So what I was saying is what I could do is so 6:30. Oops. What did I say? I started. Yeah, 6:30. Actually, hold on. Let's do this. Let's go here. Okay. Plus book equals so grocery delivery plus um, podcast on voice recorder. And so then what I'll do is that'll give me about after when it fills up about 160 hours of content, all focused on one the podcast. So right now it's just reading. So it's going to be maybe a reflection of what I'm doing, but it's defining parameters. That's the goal of it. It's specified, specific content, programming. So I'm self-programming myself, or yeah, self-programming. So then, um, once that's complete, during study time, which is after work and everything, I come home and I begin download files and upload to podcasts. And then I'll need social media to advertise when I post something. So I'll start with Twitter. Since I like Elon Musk and I just like the kind of what he's doing with the platform. It's more interesting, and especially since it's useful, I just think it'll be useful for this. And maybe set up and no, I'll wait for Instagram. Instagram, I'll wait until I start lecturing. So when I start lecturing, I'll take screenshots and upload them. So I'll have two profiles. I'll have a YouTube, and then I'll have a podcast. Cool. But yeah, that's basically what I want to do. And then because this is during study time, I'm not wasting any time. I'm actually doubling the efficiency of my time because uploading the content, uploading that 160 hours of content is going to take a little time. So, but I shouldn't have to do any editing. The goal is to read enough so that way I build that short-term, quick sort of thinking because that's basically what reading is. I'm looking slightly ahead and then translating it using my words. But Um, and then I could start getting into like more original things. I could start getting into the animation project that I want to do. Maybe some instruments. I've always wanted to learn to play the violin. But what I could do first is I could play around with some sort of digital um, program using just keyboard, mouse, and all that stuff. Actually, I do have a gaming keypad that's meant for games to hotkey keys for games like StarCraft and stuff, so you can just quickly touch them and everything. I wonder if I could find that. If I could find that, I could probably develop an art style with that. Interesting. Okay, I'll have to look at that. That might have been a good buy after all. Okay, so but needless to say, that's just a little update. I'm going to go ahead and go back to chemistry and go ahead and do the third chapter. Chapter 3, Composition of Substances and Solutions. 3.1, Formula Mass and the Mole Concept. 3.2, Empirical and Molecular Formulas. 3.3, Molarity. 3.4, Other Units for Solution Concentrations. Introduction. Swimming pools have long been a popular means of recreation, exercise, and physical therapy. Since it is impractical to refill large pools with fresh water on a frequent basis, pool water is regularly treated with chemicals to prevent the growth of harmful bacteria and algae. Proper pool maintenance requires regular additions of various chemicals, compounds, in various measured amounts. For example, the relative amount of calcium ion Ca2 in the water should be maintained within certain limits to prevent eye irritation and avoid damage to the pool bed and plumbing. To maintain proper calcium levels, calcium cations are added to the water in the form of an ionic compound that also contains anions. Thus, it is necessary to know both the relative amount of calcium in the compound and the volume of water in the pool in order to achieve the proper calcium level. Quantitative aspects of the composition of substances, such as the calcium-containing compound, and mixtures, such as the pool water, are the subject of this chapter. 3.1, Formula Mass and the Mole Concept. By the end of this section, you'll be able to calculate formula masses for covalent and ionic compounds, define the amount, unit mole, and the related quantity, Avogadro's number, explain the relation between mass, moles, and numbers of atoms or molecules, and perform calculations deriving these quantities from one another. Many argue that modern chemical science began when scientists started exploring the quantitative as well as the qualitative aspects of chemistry. For example, Dalton's atomic theory was an attempt to explain the results of measurements that allowed him to calculate the relative masses of elements combined in various compounds. Understanding the relationship between the masses of atoms and the chemical formulas of compounds allows us to quantitatively describe the composition of substances. Formula mass. An earlier chapter of this text described the development of the atomic mass unit, the concept of average atomic masses, and the use of chemical formulas to represent the elemental makeup of substances. These ideas can be extended to calculate the formula mass of a substance by summing the average atomic masses of all the atoms represented in the substance formula. Formula mass for covalent substances. For covalent substances, the formula represents the numbers and types of atoms composing of a single molecule of the substance. Therefore, the formula mass may be correctly referred to as a molecular mass. Consider chloroform, CHCl3, a covalent compound once used as a surgical anesthetic and now primarily used in the production of tetrafluoroethylene. The building block for the anti-stick polymer, Teflon. The molecular formula of chloroform indicates that a single molecule contains one carbon atom, one hydrogen atom, and 3 chlorine atoms. The average molecular mass of a chloroform molecule is therefore equal to the sum of the average atomic masses of these atoms. Figure 3.2 outlines the calculations used to derive the molecular mass of chloroform, which is 119.37 AMU. Likewise, the molecular mass of an aspirin molecule, C9H8O4, is the sum of the atomic masses of 9 carbon atoms, 8 hydrogen atoms, and 4 oxygen atoms, which amounts to 180.15 AMU. Ouch. Hold on. I'm going to pause for a second. I just had a sharp pain in my leg. All right, I'm back. It was just I had these pains a lot when I was eating terribly. And I think because I'm trying to get back on the eating better, it's starting to reach that point again. Okay. Formula mass for ionic compounds. Ionic compounds are composed of discrete cations and anions combined in ratios to yield electrically neutral bulk matter. The formula mass for an ionic compound is calculated in the same way as the formula mass for covalent compounds by summing the average atomic masses of all the atoms in the compound's formula. Keep in mind, however, that the formula for an ionic compound does not represent the composition of a discrete molecule, so it may not correctly be referred to as the molecular mass. As an example, consider sodium chloride, NaCl. The chemical name for common cable salt, sodium chloride, is an ionic compound composed of sodium cations, Na+, and chloride anion, Cl-, combined in a 1-to-1 ratio. The formula mass for this compound is computed at 58.44 AMU. Note that the average masses of neutral sodium and chlorine atoms were used in this computation rather than the masses for sodium cations and chlorine anions. This approach is perfectly acceptable when computing the formula mass of an ionic compound. Even though the sodium cation has a slightly smaller mass than a sodium atom, since it is missing an electron, this difference will be offset by the fact that a chloride anion is slightly more massive than a chloride atom due to the extra electron. Moreover, the mass of an electron is negligibly small with respect to the mass of a typical atom, even when calculating the mass of an isolated ion. The missing or additional electrons can generally be ignored since their contribution to the overall mass is negligible, reflected only in the non-significant digits that will be lost when the computed mass is properly rounded. The few exceptions to this guideline are very light ions derived from elements with precisely known atomic masses. The mole. The identity of a substance is defined not only by the types of atoms or ions it contains, but by the quantity of each type of atom or ion. For example, water, H2O, and hydrogen peroxide, H2O2, are alike in their respective molecules, are composed of hydrogen and oxygen atoms. However, because a hydrogen peroxide molecule contains 2 oxygen atoms as opposed to the water molecule, which has only 1, the 2 substances exhibit very different properties. Today, sophisticated instruments allow the direct measurement of these defining microscopic traits. However, the same traits were originally derived from the measurement of macroscopic properties, the masses and volumes of bulk quantities of matter, using relatively simple tools, balances, and volumetric glassware. This experimental approach required the introduction of a new unit for amount of substances, the mole, which remains indispensable in modern chemical science. The mole is an amount unit similar to familiar units like pair, dozen, gross, etc. It provides a specific measure of the number of atoms or molecules in a sample of matter. One Latin connotation for the word mole is a large mass or bulk, which is consistent with its use as the name for this unit. The mole provides a link between an easily measured macroscopic property, bulk mass, an extremely important fundamental property, number of atoms, molecules, and so forth. A mole of substance is that amount in which there are 6.022140076 times 10 to the 23rd discrete entities, atoms, or molecules. This large number is a fundamental constant known as Avogadro's number, or the Avogadro constant, in honor of Italian scientist Amedeo Avogadro. This constant is properly reported with an explicit unit of per mole, a conveniently rounded version being 6.022 times 10 to the 23 per mole. Consistent with its definition as an amount unit, 1 mole of any element contains the same number of atoms as 1 mole of any other element. The masses of 1 mole of different elements, however, are different Since the masses of the individual atoms are drastically different, the molar mass of an element or compound is the mass in 1 grams of mole of that substance, a property expressed in units of grams per mole, G per mole. The molar mass of any substance is numerically equivalent to its atomic or formula weight in AMU. Per the AMU definition, a single carbon-12 atom weighs 12 AMU. Its atomic mass is 12 AMU. A mole of carbon-12 weighs 12 grams. Its molar mass is 12 grams per mole. This relationship holds for all elements, since their atomic masses are measured relative to that of the AMU reference substance, carbon-12. Extending this principle, the molar mass of a compound in grams is likewise numerically equivalent to its formula mass in AMU. While atomic mass and molar mass are numerically equivalent, keep in mind that they are vastly different in terms of scale, as represented by the vast difference in the magnitudes of their respective units, AMU versus grams. To appreciate the enormity of the mole, consider a drop of water weighing about 0.03 grams. Although this represents just a tiny fraction of 1 mole of water, it contains more water molecules than can be clearly imagined. If the molecules were distributed equally among the roughly 7 billion people on Earth, each person would receive more than 100 billion molecules. The relationship between formula mass, the mole, and Avogadro's number can be applied to compute various quantities that describe the composition of substances and compounds, as demonstrated in the next several example problems. Lots of examples, holy crap. Three point two, determining empirical and molecular formulas. By the end of this section, you'll be able to compute the percent composition of a compound, determine the empirical formula of a compound, determine the molecular formula of a compound. The previous section discussed the relationship between the bulk mass of a substance and the number of atoms or molecules it contains. Given the chemical formula of the substance, one may determine the amount of the substance from its mass and vice versa. But what if the chemical formula of a substance is unknown? In this section, the same principles will be applied to derive the chemical formulas of unknown substances from experimental mass measurements. Percent composition. The elemental makeup of a compound defines its chemical identity, and chemical formulas are the most succinct way of representing this elemental makeup. When a compound's formula is known, measuring the mass of each is its constituent elements is often the first step in the process of determining the formula experimentally. The results of these measurements permit the calculation of the compound's percent composition, defined as the percent by mass of each element in the compound. For example, consider a gaseous compound composed solely of carbon and hydrogen. The percent composition of this compound could be represented as follows. Percent hydrogen equals mass H over mass compound times 100. Percent C equals mass C over mass compound times 100. If analysis of a 10-gram sample of this gas showed it contained 2.5 grams of hydrogen and 7.5 grams carbon, the percent composition would be calculated to be 25% hydrogen and 75% carbon. So, percent hydrogen equals 2.5 grams of hydrogen over 10 grams compound times 100 equals 25%. And then you can do the same with carbon. Determining percent composition from molecular or empirical formulas. Percent composition is also useful for evaluating the relative abundance of a given element in different compounds of known formulas. As one example, consider the common nitrogen-containing fertilizer ammonia, ammonium nitrate, and urea. The element nitrogen is the active ingredient for agricultural purposes, so the mass percentage of nitrogen in the compound is a practical and economic concern for consumers choosing among these fertilizers. For these sorts of applications, the percent composition of a compound is easily derived from its molecular mass and the atomic masses of its constituent elements. A molecule of NH3 contains one atom weighing 14.01 AMU and three atoms weighing a total of 3 times 1.008 AMU equals 3.024 AMU. The formula mass of ammonia is therefore 14.01 AMU plus 3.024 AMU equals 17.03 AMU, and its percent composition is, and then there's the calculations. You get 83% almost, and about 18%. This same approach may be taken considering a pair of molecules, a dozen molecules, or a mole of molecules, etc. The latter amount is most convenient and would simply involve the use of molar masses instead of atomic and formula masses, as demonstrated in example 3.10. As long as the molecular or empirical formula of the compound in question is known, the percent composition may be derived from the atomic or molecular masses of the compound's elements. Determination of empirical formulas. As previously mentioned, the most common approach to determining a compound's chemical formula is to first measure the masses of its constituent elements. However, keep in mind that chemical formulas represent the relative numbers, not masses, of atoms in the substance. Therefore, any experimentally derived data involving mass must be used to derive the corresponding numbers of atoms in the compound. This is accomplished using molar masses to convert the mass of each element to a number of moles. These molar amounts are used to compute whole number ratios that can be used to derive the empirical formula of the substance. Consider a sample of compounds determined to contain 1.71 grams of carbon and 0.287 grams of hydrogen. Corresponding numbers of atoms and moles are, there's calculations, and there's the answers. Thus, these compounds may be represented by the formula C 0.142, H 0.284. Per convention, formulas contain whole number subscripts, which can be achieved by dividing each subscript by the smaller subscript. And then you see the calculation, or CH2. Recall that subscripts of 1 are not written, but rather assumed if no other number is present. The empirical formula for this compound is thus CH2. This may or may not be the compound's molecular formula as well. However, additional information is needed to make that determination, as discussed later in the section. Consider as another example a sample of compound determined to contain 5.31 grams of chlorine and 8.4 grams of oxygen. Following the same approach yields a tentative empirical formula of C 0.150, O 0.525. You use some division, you get Cl O 3.5. In this case, dividing by the smallest subscript still leaves us with a decimal subscript in the empirical formula. To convert this into a whole number, multiply each of the subscripts by 2, retaining the same atom ratio and yielding Cl2O7 as the final empirical formula. In summary, empirical formulas are derived from experimentally measured element masses by 1. Deriving the number of molecules of each element from its mass. 2. Dividing each element's molar amount by the smallest molar amount to yield subscripts for a tentative empirical formula. 3. Multiplying all coefficients by an integer if necessary to ensure that the smallest whole number ratio of subscripts is obtained. Figure 311 outlines this procedure in flowchart fashion for a substance containing elements A and X. Derivation of molecular formulas. Recall that empirical formulas are symbols representing the relative numbers of a compound's elements, determining the absolute numbers of atoms that compose a single molecule of a covalent compound, requires knowledge of both its empirical formula and its molecular mass or molar mass. These quantities may be determined experimentally by various measurement techniques. Molecular mass, for example, is often derived from the mass spectrum of the compound. See discussion of this technique in the previous chapter on atoms and molecules. Molar mass can be measured by a number of experimental methods, many of which will be introduced in later chapters of this text. Molecular formulas are derived by comparing the compound's molecular or molar mass to its empirical formula mass. As the name suggests, an empirical formula mass is the sum of the average atomic masses of all the atoms represented in an empirical formula. If the molecular or molar mass of the substance is known, it may be divided by the empirical formula mass to yield the number of empirical formula units per molecule. There's the calculation. The molecular formula is then obtained by multiplying each subscript in the empirical formula by n, as shown by the generic empirical formula AXBY. For example, consider a covalent compound whose empirical formula is determined to be CH2O. The empirical formula mass for this compound is approximately 30 AMU. The sum of 12 AMU for one carbon atom, 2 AMU for hydrogen atoms, and 16 AMU for one oxygen atom If the compound's molecular mass is determined to be 180 AMU, this indicates that the molecules of the compound contain 6 times the number of atoms represented in the empirical formula. Molecules of this compound are then represented by molecular formulas whose subscripts are 6 times greater than those in the empirical formula. Note that this same approach may be used when the molar mass when the molar mass instead of the molecular mass is used. In this case, 1 mole of empirical formula units and molecules is considered, as opposed to single units and molecules. 3.3, molarity. By the end of this section, you'll be able to describe the fundamental properties of solutions, calculate solution concentrations using molarity, perform dilation calculations using the dilution equation. Preceding sections in this chapter focus on the composition of substances, samples of matter that contain only one type of element or compound. However, mixtures, samples of matter containing 2 or more substances physically combined, are more commonly encountered in nature than are pure substances. Similar to a pure substance, the relative composition of a mixture plays an important role in determining its properties. The relative amount of oxygen in a planet's atmosphere determines its ability to sustain aerobic life. The relative amounts of iron, carbon, nickel, and other elements in steel, a mixture known as an alloy, determine its physical strength and resistance to corrosion. The relative amount of the active ingredient in a medicine determines its effectiveness in achieving the desired pharmacological effect. The relative amount of sugar in a beverage determines its sweetness. This section will describe one of the most common ways in which the relative compositions of mixtures may be quantified. Solutions. Solutions have previously been defined as homogeneous mixtures, meaning that the composition of the mixture, and therefore its properties, is uniform throughout its entire volume. Solutions occur frequently in nature and have also been implemented in many forms of man-made technology. A more thorough treatment of solution properties is provided in the chapter on solutions and colloids, but provided here is an introduction to some of the basic properties of solutions. The relative amount of a given solution component is known as its concentration. Often, though not always, a solution contains one component with a concentration that is significantly greater than that of all other components. This component is called the solvent and may be viewed as the medium in which the other components are dispersed or dissolved. Solutions in which water is the solvent are, of course, very common on our planet. A solution in which water is the solvent is called an aqueous solution. A solute is the component of a solution that is typically present at a much lower concentration than the solvent. Solute concentrations are often described with qualitative terms such as dilute, a relatively low concentration, and concentrated, a relatively high concentration. Concentrations may be quantitatively assessed using a wide variety of measurement units, each convenient for particular applications. Molarity, M, is a useful concentration unit for many applications in chemistry. Molarity is defined as the number of moles of solute in exactly 1 liter of the solution. Moles equals mole solute per liter solution. When performing calculations stepwise, as in example 317, it is important to refrain from rounding any intermediate calculation results, which can lead to rounding errors in the final result. In example 317, the molar amount of NaCl computed in the first step, 1.325 moles, would be properly rounded to 1.32 moles if it were to be reported. However, although the last digit is not significant, it must be retained as a guard digit in the intermediate calculation. If the guard digit had not been retained, the final calculation for the mass of NaCl would have been 77.1 grams, a difference of 0.3 grams. In addition to retaining a guard digit for intermediate calculations, rounding errors may also be avoided by performing computations in a single step. This eliminates intermediate steps so that only the final result is rounded. Dilution of solutions. Dilution is the process whereby the concentration of a solution is lessened by the addition of solvents. For example, a glass of iced tea becomes increasingly diluted as the ice melts. The water from the melting ice increases the volume of the solvent and the overall volume of the solution, thereby reducing the relative concentrations of the solutes that give the beverage its taste. Dilution is also a common means of preparing solutions of a desired concentration. By adding solvent to a measured portion of a more concentrated stock solution, a solution of lesser concentration may be prepared. For example, commercial pesticides are typically sold as solutions in which the active ingredients are far more concentrated than is appropriate for their application. Before they can be used on crops, the pesticide must be diluted. This is also a very common practice for the preparation of a number of common laboratory reagents. A simple mathematical relationship can be used to relate the volumes and concentrations of a solution before and after the dilution process. According to the definition of molarity, the number of moles of solute in a solution is equal to the product of the solution's molarity and its volume in liters. Expressions like these may be written for a solution before and after it is diluted, where the subscripts 1 and 2 refer to the solution before and after the dilution, respectively. Since the dilution process does not change the amount of solute in the solution, N1 equals N2. Thus, these two equations may be set equal to one another. This relation is commonly referred to as the dilution equation. Although this equation uses molarity as the unit of concentration and liters as the unit of volume, other units of concentration and volume may be used as long as the units properly cancel per the factor label method. Reflecting this versatility, the dilution equation is often written in the more general form, C1V1 equals C2V2, where C and V are concentration and volume, respectively. Three, four. Other units for solution concentrations. By the end of the section, you'll be able to find the concentration units of mass percentage, mass to volume percentage, parts per million, and parts per billion. Perform computations relating a solution's concentration and its components, volumes, and or masses using these units. The previous sec. The previous section introduced molarity, a very useful measurement unit for evaluating the concentration of solutions. However, molarity is only one measure of concentration. This section will describe some other units of concentration that are commonly used in various applications, either for convenience or by convention. Hold on, I need to get my glasses on. I keep forgetting to put them on. I'm sorry. Okay. That's better. Okay. This section will describe some other units of concentration that are commonly used in various applications, either for convenience or by convention. Mass percentage. Earlier in this chapter, percent composition was introduced as a measure of the relative amount of a given element in a compound. Percentages are also commonly used to express the composition of mixtures, including solutions. The mass percentage of a solution component is defined as the ratio of the component's mass to the solution's mass, expressed as a percentage. Mass percentage is also referred to by similar names such as percent mass, percent weight, weight to weight, percent, and other variations on this theme. The most common symbol for mass percentage is simply the percent sign. Hold on. Although more detailed symbols are often used, including percent mass, percent weight, and WW%. Use of these more detailed symbols can prevent confusion of mass percentages with other types of percentages, such as volume percentages, to be discussed later in the section. Mass percentages are popular concentration units for consumer products. The label of a typical liquid bleach bottle cites the concentration of its active ingredient, sodium hypochlorite, as being 7.4%. A 100.0 gram sample of bleach would therefore contain 7.4 grams of NaOCl. Volume percentage. Liquid volumes over a wide range of magnitudes are conveniently measured using common and relatively inexpensive laboratory equipment. The concentration of a solution formed by dissolving a liquid solute in a liquid solvent is therefore often expressed as a volume percentage, percent vol, or V to V percent. Mass volume percent. Mixed percentage units derived from The mass of solute and the volume of solution are popular for certain biochemical and medical applications. A mass to volume percent is a ratio of the solute's mass to the solution's volume expressed as a percentage. The specific units used for solute mass and solution volume may vary depending on the solution. For example, physiological saline solution used to prepare intravenous fluids has a concentration of 0.9% mass to volume, indicating that the composition is 0.9% grams or zero point 0.9 grams of solute per 100 milliliters of solution. The concentration of glucose in blood, commonly referred to as blood sugar, is also typically expressed in terms of a mass to volume ratio. Though not expressed explicitly as a percentage, its concentration is usually given in milligrams of glucose per deciliter of blood. Parts per million and parts per billion. Very low solute concentrations are often expressed using appropriately small units such as parts per million or parts per billion. Like percentage units, ppm and ppb may be defined in terms of masses, volumes, or mixed mass to volume units. There are also ppm and ppb units defined with respect to numbers of atoms and molecules. The mass based on definitions of ppm and ppb are given here. Both ppm and ppb are convenient units for reporting the concentration of pollutants and other trace contaminants in water. Concentrations of these contaminants are typically very low in treated and natural water, and their levels cannot exceed relatively low concentration thresholds without causing adverse effects on health and wildlife. For example, the EPA has identified the maximum safe level of fluoride ion in tap water to be 4 ppm. Inline water filters are designed to reduce the concentration of fluoride and several other trace level contaminants in tap water. All right, and that's it. Chapter 3.